So this time we're taking a look at section 6.3, which deals with volumes by cylindrical shells. So maybe we have a picture that looks something like this. Let's say we have our y equals f of x, and maybe this curve is a top boundary for this region, bounded below by the x-axis. And maybe you have some sort of intersection of the curve with the x-axis at x equals b, and of course the way I have it drawn looks like maybe there's intersection at x equals 0 as well. But let's suppose that what we're interested in doing is revolving this region here about the y-axis. Now in the previous section we took a look at the disk method and the washer method, and so in a situation like this, the kind of solid that we would expect revolving about the y-axis, we would end up using the washer method. Because if you take a look at, let's say, the mirror image of this region about the y-axis, getting a picture that perhaps looks something like this. And if we were to take a look at some sort of y value, and take a look at the cross section, we get this washer. Problem that we're running into, though, is that when we take a look at the inner radius and we take a look at the outer radius, we're going to have to think about this y equals f of x a little differently. Because if we're going to be integrating with respect to y, we're going to need to think of this piece of the curve here as x equals some function in terms of y, and this piece of the curve here as x equals some function in terms of y, and that could be rather problematic. So instead of looking at the washer method in a case like this, we're going to do something a bit different. So let's take a look at a similar picture. Maybe we have a mirror image once again. Okay, the solid revolution. And what we're going to do, instead of using washers, is we're going to use what are called cylindrical shells. So if this original region, let's say, goes from x equals 0 to x equals b, or in general from x equals a to x equals b, where a and b are non-negative, we can start thinking about partitioning our interval into subintervals of equal width. And we've seen this song and dance before on a number of occasions. Let's say we take a look at some sort of subinterval I, and so this boundary we'll call x sub I minus 1. This boundary we'll call x sub I. And we're going to need to take a representative point from subinterval I, but this time our representative point is actually going to be the midpoint of the given subinterval. So we're going to call that midpoint x sub I bar. So x sub I bar. Now, keep in mind, once again, that this boundary here is y equals f of x. So we take the x sub I bar, we plug it into this function, it gives us a particular height, which is actually going to be the height of a rectangle that we're going to produce over subinterval I. Now the height of that rectangle is f of xi bar. The width is delta x. But see, what's happening is we're taking a look at this region here, and we're revolving it about the y-axis. So if we're trying to get some sort of representation for the volume of that resulting solid, then one of the things we're going to do is we're going to take this rectangle, we're going to revolve it about the y-axis. And what's going to happen is we're going to get a cylindrical shell that's produced. And that cylindrical shell is going to have a volume that's going to approximate the volume of this little part of our region revolved about the y-axis. So the cylindrical shell, you draw it out. You get a picture that perhaps looks something like the following. So I got a mirror image on the other side of the y-axis, and we'll have a picture that looks kind of like this. So we want to figure out what is the volume of that cylindrical shell. Well, one way to really think about the volume is to consider what would happen if you were to cut the shell like so and unwrap it. Now what you would get would be something that looks a bit like a rectangular solid. Cut the shell, unroll it. The height is going to be f of xi bar. There's going to be a certain thickness as well. That thickness is going to be given to us by delta x, is the width of our subinterval. But the distance across here is going to be the same as the circumference of basically the average of the two radii, inner radius and the outer radius of the cylinder. Well, that's where our xi bar comes in, so if we take a look at this along the top, and we're taking a measure of, well, circumference with a radius of xi bar. So the distance from the axis revolution to here will be xi bar. So 2 pi times radius, 2 pi times xi bar. And so we'll take the volume of this shell I will be v sub I, which is going to be our length times width times height. It's going to be 2 pi times xi bar times f of xi bar times delta x. Now, we would have to do this same sort of thing for every single one of the subintervals in our partition. Not just subinterval I, but all the subintervals from I equals 1 to n. And so if we were to get an estimate for the volume of the solid revolution, then V would be approximately equal to summation I equals 1 to n of the V sub i's, which is the summation I equals 1 to n of 2 pi xi bar f of xi bar times delta x. So that would be an approximation for our volume of the solid revolution. However, if you want the actual volume, you'll take the limit as n approaches infinity of this thing, and that'll lead us to the following observation. Which is the volume of the solid obtained By rotating about the y-axis, the region under the curve y equals f of x from A to B. Well, remember, the volume would actually equal the limit as n approaches infinity of the sum, but we can recognize that as the integral from A to B of 2 pi x times f of x dx. And that's what our volume formula looks like. Integral from A to B, 2 pi x times f of x dx. And of course, we're going to want to specify A is greater than or equal to 0 and less than B. All right, so if you're wondering about the A greater than or equal to 0, less than B, well, the A less than B I think is probably pretty obvious. A greater than or equal to 0 is, imagine what would happen instead of having the y-axis here, we have the y-axis here, and we start trying to revolve about the y-axis. We'll end up having, over a half revolution, the solid will end up essentially running into itself. So we avoid that situation if we make these conditions on A and B. So let's take a look at a specific example. And so for this example, we're going to find the volume of the solid. Obtained by rotating about the y-axis. The region bounded by y equals 2x squared minus x cubed, and y equals 0. Well, our y equals 0 is the x-axis. And so we take a look at this y equals 2x squared minus x cubed. Probably not a bad idea to draw a picture. But really what we're mostly interested in is sort of a general idea of what this graph looks like. Now, you can figure out where y equals 2x squared minus x cubed intersects the x-axis by setting y equal to 0 and solving for x. So what you would get is 2x squared minus x cubed equals 0. But if you factor an x squared out of each of these terms, you get a 2 from the first term and a minus x from the second. And then when you set each of these equal to 0, x squared equals 0 means x is 0. 2 minus x equals 0 means x is 2. And so we know that this graph is going to cross it's going to intersect the x-axis at 0 and 2. And if you take a look at what the graph actually looks like, you're going to get a picture that's similar to this. And so the interval over which this region lies is the x interval from 0 to 2. We've got our y equals 2x squared minus x cubed. And we're going to, once again, we're going to revolve this region about the y-axis. Once again, revolving about the y-axis. we would have some sort of mirror image for this. And so perhaps this mirror image looks something like the following. What we're really interested in figuring out is what a typical shell is going to look like. And so I choose some sort of x value from 0 to 2. Maybe the x value is sitting right there. And I draw a shell. I'm really interested in two things regarding the shell. Shell radius and shell height. You see, what you have to remember about this little note is that here we were describing the volume of a solid obtained by rotating about the y-axis, the region under the curve y equals f of x from A to B. Now this is precisely the kind of situation we find ourselves in here. Now in this case, the shell radius, what we're going to end up getting is you're taking the distance from the axis of revolution to the shell, and that distance is just x. So shell radius is x. Shell height, well in this case, distance from the x-axis to the curve, that's going to be your y value, 2x squared minus x cubed. So when we take a look at the volume, we know the region lies over the interval from 0 to 2. And then we have 2 pi times the shell radius, which is x, times the shell height, which is a 2x squared minus x cubed. So we make a little bit more room. So we can finish this out. So we have an integral from 0 to 2. We got the 2 pi, and then you can multiply the x through here. X times 2x squared gives you 2x cubed. And then x times negative x cubed gives you negative x to the 4th. So now we're interested in figuring out how to integrate this thing. So we're going to 2 pi times, and then we'll have integral of 2x cubed, 2x to the 4th over 4, or 1/2 x to the 4th. Integrate the negative x to the 4th, you get a negative 1/5 x to the 5th. And we take that, of course, over the x interval from 0 to 2. So we're going to be plugging in 2 for x, and then we'll subtract what we get when we plug in 0 for x. Well, if you plug in 2 for x, you're going to get 2 pi times half times 2 to the 4th minus 5th times 2 to the 5th. But subtracting what you get when you plug in 0 for x, well, plugging in 0 for x, you're just going to get 0. So volume is going to be 2 pi times, and then 2 to the 4th gives you 16, times a half gives you 8. 2 to the 5th is 32, times negative 1/5 gives you a negative 32 fifths. Now, 8 is the same thing as 40 over 5. You subtract 32 over 5 from that, you get 8 over 5. So 2 pi times 8 fifths, which means that our volume is 16 pi over 5. All And so, let's take a look at another example. So in this case, we're going to find the volume of the solid. That's going to be obtained by rotating about the y-axis. The region between y equals x and y equals x squared. Now, if you're thinking that this seems a bit on the familiar side, well, it is, because in the previous section we looked at things very similar to this. But once again, we're doing a rotation about the y-axis. Let's take a look at our region. So y equals x. What are our boundaries? Y equals x squared is our other boundary. And so the region that we're going to be rotating about the y-axis is this region here. And of course we can take a look at a mirror image. Our mirror image will have a picture that looks something like this. So if you think about what the actual solid might look like, kind of a bowl shape like this, but you'll have sides kind of go in like so. So we think about what a typical shell would look like, and we're going to take some sort of x value between 0 and 1, and we'll draw that shell. We're interested in the shell radius as well as the shell height. Now, given that we're still revolving about the y-axis, shell radius is going to be the distance from the axis of revolution to the shell, and that distance is x. But remember, the curves that we have are y equals x and y equals x squared. So the shell height isn't going to be x, and it's not going to be x squared. It's actually going to be the difference in those. So x minus x squared would actually be your shell height in this case. Basically, if you were to take the distance from the x-axis to the top curve, that would be x, but that would be too much for the height. So you subtract away the distance from the x-axis to the bottom curve. So you're subtracting away x squared. So x minus x squared gives you that shell height. And so when we think about putting this all together to get our integral, we have volume is equal to integral from 0 to 1, because that's the x interval over which the original region lies. You'll have 2 pi times your shell radius, which is x, times your shell height, which is x minus x squared. And so we multiply the x by the x minus x squared. We'll have v is equal to integral from 0 to 1, 2 pi times x gives you x squared. X times a negative x squared gives you a negative x cubed. So we'll get 2 pi times, integrate the x squared, you get a third x cubed. Integrate the negative x cubed, you get minus a fourth x to the fourth. So now we're going to have to plug in 1 for x, and then subtract what we get when we plug in 0 for x. But plugging in 1 for x, you'll get a 1/3 minus a 1/4. And then if you plug in 0 for x, you're just going to get 0. So that's pretty good. The fractions you have here are 1/3 and 1/4. We're subtracting the fourths from a third. So let's go ahead and get a common denominator of 12. So 1/3 we know is the same as 4/12. 1/4 we know is the same as 3/12. So volume is going to be 2 pi times the 12th, or pi over 6. So I have one more example I'd like to show you. And in this example, we're going to shift the axis of revolution. So this time we'll find the volume of the solid. That's obtained by rotating the region bounded by y equals x minus x squared, and y equals 0. About the line x equals 2. So let's take a look at a picture. So we have our axis revolution, x equals 2. And we also know that y equals 0 is our x-axis. And y equals x minus x squared, well, that's going to be a parabola. But if you think about figuring out where the parabola crosses the x-axis, set y equal to 0 and solve for x. So you would get x minus x squared is equal to 0. Factor out an x, you get a 1 minus x as the other factor. So that means that parabola is going to cross the x-axis, x equals 0 and x equals 1. And so you're going to get a picture that looks something like this. So this region, once again, y equals x minus x squared. gets revolved about x equals 2. So the mirror image of this picture is going to look something like the following. Now our original region, of course, goes from 0 to 1 xy's. And so I'm interested in figuring out some x location somewhere between 0 and 1. I want to figure out what the typical shell is going to look like. Well, a typical shell is going to look something like that. So we're going to need to figure out what the shell height is and what the shell radius is. And in terms of the shell radius, we're looking at the distance from the axis of revolution to the edge of the shell. Well, if you were to take a look at the entire distance from the y-axis to the axis of revolution, that's 2 units. But you're taking away this distance of x from that to get the shell radius. So you take 2 minus x, it leaves you with this. So our shell radius is 2 minus x. Shell height here is not too bad. Shell height, you take the distance from the x-axis to the curve, and that's x minus x squared. So we can set up our integral for the volume over here. So volume integral from 0 to 1, because 0 and 1 are the endpoints of the interval over which the original region lies. We'll have 2 pi times shell radius, which is 2 minus x, times shell height, which is x minus x squared. Now, at this point, we multiply through, and we'll have a 2x minus x squared minus 2x squared plus x cubed. So 2x minus x squared minus 2x squared plus x cubed. Combine your like terms and maybe write what's in here in descending powers of the variable. And integral 0 to 1, 2 pi times x cubed minus 3x squared plus 2x. Now when we go to integrate, we'll have our 2 pi times, and then integrate the x cubed, you get a 1/4 x to the 4th. Integrate your negative 3x squared, you get a negative x cubed. Integrate your 2x, you get x squared. Now, we plug in 1 for x, and we'll have 2 pi times 4th times 1 to the 4th gives us a 4th. Minus 1 cubed is minus 1, plus 1 squared is plus 1. And then we subtract what we get when we plug in 0 for x, but that means subtracting 0. So here you have a 4th minus 1 plus 1. Well, that's a 4th. Multiply by 2 pi, and you get your final answer, pi over 2. Alright, so that finishes out this example, but I do have some remarks that I'd like to make, and mainly dealing with comparisons between the shell method and the washer and disc methods. So if we were to take a look at let's say, a problem in which we use the washer method or the disc method, and we revolved about a vertical axis, the integration is with respect to y. Because when we take a look at a washer or a disc in that case, it's dependent upon where we are y-wise. However, in the shell method, the shell is dependent upon where we are x-wise. And so revolution about a vertical axis, if we're going to find the volume of a solid revolution using the shell method, we're integrating with respect to x. Also, although I didn't do any examples, we could take a look at using the shell method when revolving about a horizontal axis, and we would, in those cases, integrate with respect to y. Having said that, 6.3 is finished. So we'll have 3, 5, 11, 15, 19, and 37.